He has claimed that if anybody were to show him an alternative hypothesis, he would tear up his paper and admit he was wrong. But at the first instance that he receives criticism, that's shown to be not true.
What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a brilliant weekend and are fired up for the week ahead. Now, last week, physicist Avi Loeb presented preliminary analysis of spherules which were dredged from the ocean floor and which he claims might have an origin outside of our solar system or even have been shedded from extraterrestrial technology. Recently, Loeb undertook an expedition to the seas northeast of Papua New Guinea to attempt to recover fragments from a fireball that blazed across the sky on January the 8th, 2014. The object's location, velocity, and brightness were recorded by US military sensors, and Loeb believes these data prove that the fireball, now dubbed IM-1, is the first ever recognized interstellar meteor, an object that crashed to Earth but with origins outside of our own solar system. During the expedition, Loeb and his team recovered hundreds of spherules using a magnetic hook trailed beneath their boat. Spherules can be created when objects crash through the atmosphere from space and rock is vaporized and expands into a giant vapor plume. Small droplets of molten rock in the plume then condense and solidify and fall to the Earth's surface, sinking to the bottom of the ocean. Now, preliminary analysis of 57 of the spherules dredged from the ocean has been completed and submitted for peer review. Loeb believes that the spherules his team recovered are fragments from IM-1 and that their composition clearly indicates that they have an origin outside of our solar system. Loeb also claims that these spherules could be shavings from a piece of extraterrestrial technology. However, spherules can also be produced by other mechanisms, such as industrial processes, nuclear fallout, and even car brakes. Many in the broader scientific community are skeptical of Loeb's claims and do not believe that he has presented sufficient evidence to support his claims, nor considered alternate hypotheses appropriately. To help me dig into these controversial claims, I'm joined by two brilliant special guests. First up, Professor Steve Desch. Professor Desch is a professor of astrophysics in the School of Earth and Space Exploration at Arizona State University. His research focuses on developing models of star and planet formation using data from meteoritics and planetary science. He especially studies the origins of chondrules and meteorites. The asteroid 9926 Desch is even named after him. Professor Desch also works in the fields of exoplanets and astrobiology, and is the principal investigator of the NASA-funded NEXSS grant to study geochemical cycles on exoplanets and aid in searches for signs of life on other planets. Secondly, I'm joined by Professor Larry Nittler. Professor Nittler is a cosmochemist who studies the origin and evolution of stars, the galaxy, and the solar system, both through laboratory analysis of extraterrestrial materials like meteorites and returned comet and asteroid samples, and through planetary remote sensing via spacecraft. He has played leading roles in the analysis of comet and solar wind samples returned by NASA's Stardust and Genesis missions respectively, and served as the deputy principal investigator on NASA's Messenger mission to Mercury. He is currently a NASA participating scientist on the Japanese asteroid sample return mission Hayabusa 2 and a member of the ESA-JAXA Bepi Colombo Mercury mission team. He received the Alfred O'Neill Prize of the Meteoritical Society in 2001 and was named a Fellow of the same society in 2010. Asteroid 5992 Nittler is named in his honour. So who better to help me dig into this controversial topic and see if Loeb's claims hold water or sink back to the bottom of the ocean? So we've heard a lot this week about Avi's cosmic spherules. So Steve, I'll come to you first and let's start at the beginning. Some people might be confused about what spherules are. So what are they? How are they produced? And why are we interested in studying them?
Well, it's in the name. They're little spheres of
Yep.
things that come from a variety of sources. And many of us in our community are interested in the micrometeorites, the spherules that are the product of meteors passing through the atmosphere and depositing material. A lot of it ends up on the seafloor. Much of it is stony, and some of it is metallic. And in addition to micrometeorites, there are a whole host of other origins and sources, including volcanic products and industrial products. And I'm not as familiar with them, but my oceanographer friend tells me that, no matter where you go on the seafloor, it's littered with all sorts of these things. There are, I think the technical term was squillions.
Car brakes, I heard as well, like so many different ways to get these things. So
Yeah.
they can be linked though, right, to meteors. How do they form in that case if they come from something that's come crashing through the atmosphere?
Right, they just melt off. Their meteors are ablated as they pass through the atmosphere, and the surfaces of them are melted, and the air pressure is kind of scraping material off. I'm sure Larry might have more experience with that.
No, I mean, that's basically right. You have little droplets of melt come off and they form spheres because that's what little droplets of melt like to do.
Yeah.
And they range from only barely partially melted to completely and totally melted.
Super. So that's exactly what we're going to be talking about today. And Larry, why would it be so valuable? Why would it be so interesting in scientists to get our hands on extrasolar spherules? Why would that be so intriguing? And why is this such a major finding that Avi is claiming to have found?
Well, in terms of chemistry, we know a lot, though hardly everything, about the materials in our solar system, and we know there's a huge diversity. But we know almost nothing about other solar systems. We know there's, a few you can measure the elemental composition of stars, and you can make some estimates from things about exoplanets. But for the most part, we don't really know how variable elements and isotopes are in the galaxy. We have a lot of hints and theories, but getting an actual rock from another solar system would tell us a great deal about, well, first of all, just having a rock from another solar system would tell us that it's possible for rocks to go from one solar system to another, which we believe is probably very straightforward. And now we've observed interstellar comets coming through the solar system, so we know it is possible. But actually sampling that would just give us a handle on material that there's no other way to study.
Yeah. So we can find out.
Agree.
Sorry, Steve. Yeah, please.
Yeah, I agree. It's the isotopic abundances that are key, because we can measure to some degree of accuracy the elemental abundances of stars, but we have no handle on their isotope ratios. What are the different flavors of iron or oxygen atoms, what ratios exist in other solar system. And yet these are predicted by what we call galactic chemical evolution models. So seeing how different elements and their isotopic ratios kind of relate to each other would allow us to validate those models. It would be a huge boon.
And see if our solar system is very different to others, I guess, would be a very interesting thing to learn. So Avi Loeb claims to have discovered dozens of these spherules from an extrasolar meteor that he's dubbed IM1. So I think we've got some pictures here of the spherules that he picked up from the seafloor near Papua New Guinea. And he submitted his findings for publication of some analysis of a subset of these spherules. So before we get too deep into the details of that analysis, Steve, you had a kind of 5-point plan as to what Avi should do to prove that these spherules have come from an extrasolar source. What are your thoughts on just broad view on his preprint, and how and what are those 5 steps he should go through to prove that these spherules did indeed come from an extrasolar source?
Right. So I think he's jumped the gun on multiple points. One is it's not even clear that the meteor that was observed in 2014 by satellites was even interstellar. There are suggestions that it is, but it's hardly verified, and probably not verified at the level that would warrant an expensive millions of dollars expedition.
So the first point is, if you want to say your spherules are interstellar, you need to know that your source was interstellar. So we need to prove that this meteor coming through was an interstellar meteor to start with.
Absolutely. And then the second point is that you want to know where to look. Obviously, you need to pin down the location of where the material would have been deposited. You then also need to have some confidence that the material will be concentrated in the region where you're looking. If it's spread out over, a very large area, then there's no hope for recovery, even if it did produce a considerable amount of material. There's also the point that if it were truly interstellar and going as fast as claimed, in order to claim that it was not bound to the sun and interstellar, you'd want to make sure that it didn't completely burn up in the atmosphere. And standard formulas suggest if it were going at 45 kilometers a second relative to Earth, it would have 99.9999% burned up, and you'd be left with milligrams. So there's all these questions to do with whether you could even recover a reasonable amount of material, and where to look to get it.
So if I kind of line those up in the way you did in kind of your thread on Twitter, we need to establish that this meteor is interstellar. Then we need to establish it didn't burn up. Then we need to work out where these things landed, and did Avi Loeb look in the right place. Then we need to establish, are the things that he found related to the meteor that came by? And then we need to see if the spherules themselves seem to look different to things that we produce in our solar system. So there's a nice flow through there of steps, and I believe you feel that none of those were done. Larry, do you feel the same about this preprint?
I do, and I'd say there's one more important point: is you need to show that if you find something unusual, it is unique to the area you think the meteor should be.
Yeah.
And you need to have sufficient control experiments to show that you have something interesting.
I've got your Poisson stats in here, Larry. Don't worry. We are going to be coming to those imminently. So if we start on that first point, Steve, is IM1, this meteor, interstellar? So we start at the top of that checklist. So Avi Loeb has repeatedly and vehemently asserted that IM1 is an extrasolar meteor, and this is based on US military observations. However, as you said, a lot of domain experts are not particularly convinced. What would be the evidence that would kind of cut this? I think you said a speed above 45 kilometers per second. Would that be the evidence that we're looking for?
Right. The speed relative to Earth that was reported was 45 kilometers a second. So this is data that comes from satellites. And these are satellites designed, of course, to look for rocket launches and the like. So they're not generally looking for things that are this fast. So the cadence of the observations is not necessarily designed to look for things as fast as 45 kilometers a second. And so this data is collected by the Department of Defense, and then it is sometimes reported to the JPL, Center for Near Earth Object Studies database. But it's not done in an automated way or in a way that guarantees that there are no errors. And
Avi's got quite upset about this, right? Where people have said, he said, I've got a letter from the military, I've got a letter from NASA saying that, this is all above board, the readings are correct, there's no errors in the readings. But you pointed to a couple of papers and some studies that suggest not all of the velocity vectors, not all of the timings in these data sets from the military are necessarily accurate, given civilian sources that have tried to check these data sets.
Exactly. So yeah, you've pulled up this paper by de Villepoix et al. And there are a few dozen meteors that are in the database that could be checked by ground-based networks, people who have set up cameras. Sometimes they incorporate radar data. And these are much more accurate and precise, and especially because you have multiple sensors and you can triangulate things. And these surveys show that most of what is in the database is fine, but and the database doesn't report uncertainties or error bars, but you can infer, based on the relative matches that they are reasonable few kilometers a second sort of errors for slow things. But then as you look at faster objects, the error bars get bigger because the mismatches increase. And this shows that about a third of the time, though, the velocities don't match really at all. And the directions especially are in 90 degrees apart sometimes.
So in cases where we can check the military data with civilian technology, there seem to be some errors in the military data, and therefore why should we be incredibly confident that this time they've got it exactly right and we know exactly where to look for this meteor? Is that
a third of the time? A third of the time, the way the data are reported to this database introduce errors. Yes.
And is that, if we go to the particular case of IM1, is there any reason to believe that's the case in this case, or that IM1 is more consistent with being from our solar system than outside?
Right. So Peter Brown has published a paper and analyzing the data with exactly that question in mind, and has concluded that, among other things, almost any object you put in on a 45 kilometers a second velocity would have burned up higher in the atmosphere. You should have seen a signal at much greater altitude, and infers that probably 25 kilometers a second would be consistent with the error bars that they infer for these sorts of fast meteors and a lot of aspects of the light curve. And then Maria Hajdukova et al., someone I'm collaborating with, they're doing a similar analysis that'll be submitted soon. And in that paper, they look at the velocity components themselves and of the fast meteors, and they find something wonky usually with one or the other. And there's something wrong about how the data reported for the fast meteors. It's just too easy to make a mistake with a velocity component when they're going really fast.
And Larry, Avi's pushed back on this and said, this is the military. They're supposed to be defending us. Like, they must be the best data, but surely they're not. Are they set up to do these kind of measurements on meteors that are coming into the atmosphere?
Well, I'm not personally familiar with the equipment they use, what they do. But it's not a scientific argument to say that somebody said it's right, so it's right. It doesn't matter whether it's the military or a professor from Harvard University, And
this would be something he would usually say, right? He would say, I'm not going to rely on the government or somebody to tell me. I think it might be something like aliens. Yeah. So this would usually be his argument.
It's related to the fallacy of the appeal to authority, right? And it is fallacious to just say this person's an authority, they say it, therefore it's right. As scientists, we need to look at the evidence itself and the measurements themselves. And as Steve said, there's a lot of evidence by comparing with networks that are designed to do these kind of measurements that show that what the DoD is using is not adequate for these things. This is not to say that it absolutely cannot be an interstellar meteor, but that it's very unlikely, and that it's on Professor Loeb and his colleagues to prove that.
They have the burden of proof to actually show that this damn thing is what they say. No, that's perfectly fair. So this first pillar of, is this an interstellar meteor, is still kind of up in the air, and people aren't particularly convinced. Larry, the second point was this idea that we mentioned, that at 45 kilometers per hour, even if this thing was made out of iron, you'd expect, I think Steve said 99.9999, 4 nines after there, might be more, percent of it to have burnt up. So the idea that Avi can go and kind of drop the sled and find something straight away, that seems like he's found a needle in a haystack. Is that the idea there?
Oh, absolutely. And also that ablation, I mean, that destruction will produce spherules, but it's going to be very, very high up in the atmosphere, which is part of the point of what Peter Brown's paper was. And so there's no reason to think those spheres would fall. Spherules high in the atmosphere are going to just follow the trajectory down to this extremely narrow cone down to this particular spot in the Indian Ocean. There's wind. Yeah. And then when they hit the water, they slow down, and there's currents and waves, and then it'll take them a while to settle. They're not it's not so simple that even with complete destruction, yes, you might find one somewhere on the floor of the ocean, but in the statistics, we're talking about a needle in a billion haystacks, not a needle in a haystack.
So
or a squillion.
so those first two pillars, is it interstellar, this meteor? Not sure. Would it have been completely destroyed? We're also not sure. So it's very unlikely that he would have found anything. So we're not looking good on the first two. Then I guess we go to, did the spherals come from IM1 specifically? So Larry, you sort of teed that up nicely there. Let's assume that IM1 is an extrasolar meteor and it didn't burn up, right? So is there any evidence, Steve, that the spherals that Avi has came from any meteor before we get to IM1 specifically? Are we happy that they came from a meteor, full stop?
A meteor. Well, probably most of them did. They resemble this, but of course there's a background of micrometeorites that would outnumber any from this meteor by factors of thousands or tens of thousands. So you're very likely to find micrometeorites, and you're very unlikely that any of them came from any one meteor.
So it could have come from a meteor, but it could be a different meteor. Even if you have something that looks like it came from a meteor with these spherals, these dendritic structures, a loss of volatile elements, it could have come from a different meteor. Larry, Absolutely. I think you wanted to jump in.
Well, no, I mean, that's absolutely right. That even there is some the claim from Dr. Loeb is that 5 or so of the 50 they analyzed geochemically are different geochemically and therefore from IM1. But different does not mean extrasolar.
Mm-hmm. We're going to get to the composition in a minute, but yes.
Yeah, I'll get to compositionally, they are certainly consistent with being extraterrestrial, and the iron isotopic fractionations support that as well, but not. They don't strongly support it.
Mm-hmm. Fair enough, Steve. Before we get to the composition, which we are going to get to kind of next, we were talking about whether they came from a meteor, which seems we're relatively happy with. Whether they came from IM1 specifically seems like a very bold claim, given the errors that you talked about in the velocity vectors, the trajectories. Can we be certain that these spherals came from IM1? Kind of Larry teed it up that, you know, the spread of the currents, that these things don't just fall where you think they're going to do along the path. Is it a pretty bold claim for Dr. Loeb to be saying the spherals I found are definitely from IM1?
Right. So, finding a handful of unusual spherals, we don't even know that they're associated with each other. They don't even have to come from a meteor. They could come from 5 meteors. And, a lot of these claims have to do with Loeb basically saying, well, they're where I expected to find them.
Yeah.
Which, here's the street light. Of course, this is where they'd be. A lot of that, where he expected to find them is based on, the idea that they'd be concentrated in one area and that he knows where that area is. And this graph is from one of the preprints online. It's the preprint. I don't like to call it preprint. It's a rough draft because it's not peer reviewed yet. But this is trying to show that this one seismometer on Manus Island detected the airburst, which I think it probably did. This is about 300 seconds after the fireball. You see the seismometer registered a shaking consistent with sort of the level of noise you might have heard about. And by the way, this is like 90 kilometers away.
So Avi's trying to use seismometer data and bring that together with the military data to kind of refine the search area. Is that what we're seeing kind of with
so the DoD data is degraded. They report the latitude and longitude to within 0.1 degrees, which is about 11 kilometers. So there's a box that's 22 kilometers on a side, and presumably the meteor disintegrated somewhere over that, which is not to say that's where the material fell. As Larry was saying, it's distributed over a large strewn field, and it may have kept going or not, depending on the size of the particles that come off when the meteor disintegrates. But they're trying to locate where the disintegration was, at least using the seismometer data. And you would definitely record the distance if you knew the speed of sound along the path the sound took, and you knew how long after the explosion the sound reached the seismometer. And that would give you at least a circle that you could draw, and that's what he's inferred. But the circle he's drawn inside that box that the DoD reported is very thin. It's very well defined, because he believes that you can locate that to within a kilometer, less than a kilometer, and that's based on how precisely you think that when the sound signal showed up. And so they said it showed up precisely at 271 seconds after the fireball was registered in this graph. And I don't know why you would put it there instead of 5 seconds before that or 5 seconds after that.
Yeah.
So until you can pin that down, basically the seismometer doesn't give you data that's any more precise than this gigantic box that the DoD gave. And so you're really looking at, it could have fallen anywhere within this 100 square kilometers region, and he really cannot pin it down despite his protestations.
So we're not sure IM-1 was interstellar. We're not sure it didn't burn up, and we're not exactly sure where we should be looking. So that's three kind of pillars that are kind of slightly in doubt. Larry, Professor Loeb has claimed that these spherules are definitely extrasolar material, because, as you say, a subset, I think it's 5 out of 57, have what he claims to be a kind of exotic composition that we don't expect to see in the solar system. And also that the spherules are clustered along the path that he calculates, which we've said is slightly in doubt, but at least the path that he calculates for IM-1. So let's start with the composition. So Dr. Loeb claims that, I can get the graph up here, that they're in this subset of spherules, they're highly enriched in beryllium, lanthanum, and uranium, and they have a dearth of volatile elements and elements with an affinity for iron. And he claims that this makes them very dissimilar in composition to the most common solar system meteorites, and therefore that points to an extrasolar origin for the spherules. So, Larry, how do you feel about that line of argumentation using this graph we got here?
I would agree it's an unusual composition. I would say that the argument that they're different from the majority or typical composition of solar system materials is not an argument at all, because we find strange compositions all the time, both in micrometeorites and in macroscopic meteorites.
I think Steve pointed to one 20 minutes later.
Yeah, I was going to get to that. So even among the micrometeorites, there's been literature, and Steve found this paper from 6 or 7 years ago, showing micrometeorites not collected in the putative strewn field of IM-1 that show these similar geochemical trends. The lack of volatiles is probably due to the loss during the atmospheric entry, but these enrichments in uranium and thorium, beryllium are not unique to these spherules that this Harvard team found. They've been seen before. Now, the numbers here are not as enriched, right? He's talking about 1,000 times higher than chondritic uranium, which is still a very small number, by the way. These aren't like glowing pure uranium rocks. It's still there's still trace elements.
It's not like the start of The Simpsons where he's driving around.
Exactly. But the point is that it's exactly the same pattern, and patterns is what we look at in geochemistry, because especially in things like this, which are made up of multiple minerals, and the preprint, the Loeb et al. Preprint does show electron microprobe data showing chemical heterogeneity across one of these. So these are not homogeneous chemically, which means they got different phases.
Yeah.
So then you have nugget effects when you're in this very, very small thing. All you need to explain is whatever phase is carrying these larger uranium is in higher abundance than the ones that they found in the Indian Ocean compared to these. It's not a sign that it's from interstellar space. And the thing about the micrometeorites and the cosmic spherules, and one of the reasons people study them, even though we have tens of thousands of actual meteorites that are macroscopic and much, much easier to work with, is that when you look at the compositions of the cosmic spherules, we see a broader range of compositions than we do in the bigger meteorites, which means that they're a better sample of what's hitting the Earth. That we have the meteorites are a biased sample of what is actually hitting the Earth and what is present in the solar system. So by studying the cosmic spherules, we can get a better handle on what is out there. On the other hand, they've also been sitting at the bottom of the ocean interacting with the Earth. So you also have to worry about which geochemical tracers you're looking at were there in the material before it hit the atmosphere and which have been added after that. And as far as I can tell, these authors have not addressed this or even acknowledge this as an issue.
And I think, Steve, you raised that point that why do we get this particular chemistry? I think you pointed to a paper from was it from Prasad and Rudraswamy? So
why don't we go back to the graph from their paper of the elemental abundances? Yes, this one. So what I'd want to point out, I still don't see where the normalizing element is, but nevertheless, look at the peaks in this, and boy, these are really tiny elements. So I'm looking across and I see that if I were to pick up the peaks, there's one at thorium, and there's one at I'm trying to read uranium.
I'm making your eyes work hard for
and then lanthanum, and what is that, cerium, and what is this one way over here? That's
is it vanadium or something down over here?
Niobium, and then I think vanadium. Those are siderophiled, but along the elements that typically form rocks, you see those enrichments. You see depletions in some things like aluminum, magnesium, calcium, which are very common rock forming elements. And but basically you're looking at some sort of I don't know, enrichment in those key elements. The top five are like uranium, thorium, lanthanum, there's barium and niobium. And there's depletion in zinc, for example, an especially high depletion. So you go to the other paper by Rudraswamy, the enrichments are not exactly the same, and they're not in the same order exactly, but the top 5 or 6 enriched elements are the exact same ones.
Oh, this graph you mean?
Yeah, this one right here. Yeah, so you see enrichments in thorium and uranium and lanthanum, and niobium's pretty high and barium's pretty high. So here is something that was collected. These are cosmic spherules collected somewhere completely different, the Indian Ocean. And they show remarkably high enrichments. It's a factor of 100. Not quite 1,000 in the other, but the pattern is very similar, and you have the depletion in zinc and the cobalt, and these are really similar. And so whatever made these, it wasn't Interstellar Meteor 1. Whatever gave you this pattern is something that is more or less worldwide, and what they interpreted it as is that these spherules in that location in the Indian Ocean were basically reacting with the sediments around them. So the sediments are reacting with the seawater is reacting with them in that locale. And as a result, they get these enrichments. The sediments around them were enriched in these same things, uranium, thorium, etc. And I'm not sure why those sediments are enriched in that, but again, it's clearly a terrestrial process and not an interstellar source.
And I think we kind of said before we started, and Larry kind of teed it up for us, that you don't need to prove that this is exactly what happened, that it's due to a reaction. It's not even been considered by Loeb's team that this could have happened, and there are reasonable alternate hypotheses for why these enrichments and depletions could have happened that you have to consider before you go to an interstellar meteor having arrived.
Absolutely.
That was in unison. So okay, good.
And I mean, it shows that the composition they declare is unique is not unique.
Yeah. So jumping to that claim is not valid at the moment. Any thoughts on the Larry, on the raised beryllium content? Some people have been flagging that up on Twitter, and Avi Loeb claims that this could be cosmic ray spallation on the long voyage of an extrasolar meteor through the cosmos. It's been bombarded with cosmic rays so much that it's enriched all the beryllium in it, or is that speculation?
It's speculation, and totally useless speculation unless they measure the beryllium isotopes, which is because the spallation will have a very specific beryllium 10 to beryllium 11 ratio, right? As I forget the isotopic table.
9 is the stable one.
Yeah. So I'm a physicist. The periodic table's gone out of it's gone long time.
Again, you can't use an elemental abundance to argue for spallation. You need isotope ratios.
Well, yeah, the simple fact is all of that beryllium could be reaction with terrestrial, and if it is, it would be dominated by beryllium 10. With you can use beryllium. Beryllium 9 is what's on Earth. You can use beryllium 10, which is a radioactive element, to trace these things, and people like Larry can measure the amount of beryllium 10 that's in a meteoroid and infer how long it's been exposed to cosmic rays, because that's a radioactive element. It has to be sort of freshly produced by reaction with the cosmic rays. But I think it's much more reasonable to assume that the lithium and beryllium in this object are of terrestrial origin.
And Larry, that you already mentioned it, and we'll come to it now. The other kind of prong of this that Avi comes to suggest in terms of composition that these spherules are extrasolar are the iron isotope ratio. So could you tell us a little bit about what he's claiming with this graph, and how he's trying to say that this points to an extrasolar source, and why that might not be the case?
So the argument here is more that this supports an extraterrestrial source than an extrasolar source, in that iron isotopes are not fractionated very much on Earth. You pick up a rock over here, you pick up a rock on the other side, you measure their isotopes, they're very, very similar. What you see in some of these cosmic spherules are these larger variations. And this is due to fractionation. While the thing is coming through the atmosphere, you're evaporating. Evaporation actually induces a slight change in the isotopes, and that the lighter isotopes can evaporate slightly faster than the heavier ones. And you also can have something called Rayleigh distillation, which means that you've already made you've removed some of the light isotopes, so what's left is as heavy, and then it loses a little more and gets heavier and heavier. And so it would basically move up this line or down this line, depending. Up the
line.
Yeah, I was just seeing which was the normalizing isotope. But
so this gets us into space, but it doesn't get.
But the absolute key point here is all of these. Well, there's two key points here. One is that the range is really small. These delta values are in part per 1,000 difference than a standard. So we're talking the biggest variation is 0.1%. And most of them are much smaller than this. The other is they all lie precisely on this line. And this line represents what we call a mass-dependent fractionation. And that's what you expect. Okay, yeah, this is good zooming in. What this means is that all of these can be derived from any other composition on this line by a mass-dependent process. The solar system composition lies somewhere on this line. We don't know exactly where the bulk composition is, but it's probably very close to 0,0 on this plot. And that composition is based on a mixture of material from a huge number of supernovas over the billions of years before the sun formed. And so the iron isotope composition is a very specific mixture of nucleosynthetic sources. Since then, there's been billion years of evolution, and even different parts of the galaxy will experience slightly different numbers of supernovae and types. So the iron isotope composition would be expected to change with time, and this is a process called galactic chemical evolution, and also change with space. And the exact prediction of how much it would change there's predictions, but very few experimental tests of this. Again, going back to why an interstellar meteor would be valuable. But one thing we can be very, very, very certain of is it's extremely unlikely it would be the iron isotopic composition of any other solar system except would be within 0.1% of the solar system composition. It's just extremely unlikely that some star forming, 100 parsecs away, 1 billion years after the sun, is going to have experienced different nucleosynthetic history.
And is that what we're seeing in this diagram then? That these spherules that have been collected have that kind of same ratio as we see in the solar system? Is that
because they lie on this line, they all can be derived from the same bulk solar composition. And it's just like a process like evaporation will move you up and down that line, but not off the line.
Right.
We would expect a meteor from
down here or up here, or
we would expect a meteor from another solar system to be not on this line,
right,
and probably much farther away from the line in terms of absolute numbers. We don't know this 100%, but this data provides zero evidence for an extrasolar origin, and in fact, are pretty strong evidence that it is not extrasolar.
Which I think Steve flagged up in his Twitter thread. Right, this actually appears to be evidence for a solar system source, Steve. So it gets us into space potentially because we're higher up on this line than most of the rocks on the Earth. So we're up here with the spherules. That gets us into space, this fractionation that you said when it comes through the atmosphere, but it doesn't get us out of the solar system, Steve.
Right.
Exactly. So those green ones, S21, that are supposedly this unusual composition, they have an unusual amount of lanthanum or whatever, but they're iron isotopes. This as close to a fingerprint as you get, and they're telling us that they're from our solar system.
Fair enough. Yeah. So not looking good again. Now, Larry, this is your time, because we're going to talk about the Poisson stats here. So, Larry, the big point that Avi Loeb has said, he also claims that the spherules with the anomalous, what he claims to be extrasolar composition, so these 5 that we were talking about, cluster very strongly along the calculated path of IM1. So this calculated path is supposedly kind of this yellow line here in the collection area, and you don't see this strange composition that we've talked about anywhere else, and not in the control areas, these blue areas on the top and bottom that they had. So what do you make of that claim? You brought the beautiful Poisson stats, as we said. What do you make of that claim?
I make that claim as being wholly unsupported by the very, very small statistics. And the point is that they measured 50 or so spherules within that area that they think they come from, where they think they would find the interstellar spherules, and they found 5. So that means they found about 10% of the measured spherules were this unusual trace element.
So 10% of the spherules that they analyzed, they describe as odd or extrasolar.
Yes.
So we expect 10%, and then they went looking in the other areas, didn't they? So
yes, that's exactly right. But in the other areas, they only measured 8 spherules. They only report trace element data for 8. Well, that means that if they were in these rare ones, these uranium-rich ones, were in the exact same abundance in those outlying areas as they were in the middle area, you would expect to see less than 1 of those 8 spherules.
So the chances are, if it's just 10% and there's an even distribution, if you do 8 samples, the chances are you'll probably find 1 or 0. So
exactly. So or
your
2,
statistics
or 3.
are entirely consistent with there just being a flat distribution of these things. It's just you've sampled a load on one path, and of course you found some odd things because you've looked a lot there. So it looks like there's a lot of weird things here. And then you've gone around the corner and not looked very much and said, oh, well, I looked a bit, but I didn't find anything. So there's nothing weird there. It doesn't make sense. You have to do 1,000 samples here and 1,000 samples there, and then compare to get a fair test, right?
That is exactly the point. That it is very, very, given the statistics, it is just as probable that there are more of these uranium-rich spherules in those areas they call the controls as there are in the middle one. You just cannot say anything from the statistics. So their argument that there's more is meaningless. A measurement of 0 and when you expect 1 is a very probable result. And what they, you could talk a lot about what they should do to do this, except that I think the argument Steve made at the beginning of this conversation show that you shouldn't do it at all.
I think
Yeah.
Steve, you said this was really almost kind of silly that I mean, this is the first thing you do, right? You have to get a huge control sample to be able to
Yeah.
say that
Absolutely. So, the alternative hypothesis is that there's just a background of spherules in this, general area or around the world, maybe, that have this uranium-rich composition, and maybe they're 10% of all spherules. So, throughout this whole region, you could have 10% of all spherules being enriched, and they just didn't look in those other regions to test that. And there's a 45% chance, given how few things they sampled from those other regions, there's a 45% chance that they would see nothing there, and then infer there was not a zilch, zip, nada,
and that's assuming a
Like,
flat distribution. It could be even worse somewhere
Yeah.
else. Like, who knows? Like, we as Larry said, the statistics are consistent with it just being a background of the same composition everywhere, and we can't
Yeah.
distinguish between the two hypotheses, right?
I
and
would.
the
I would.
only the only fair thing to do, the only good experimental design would have been to go somewhere where you're very positive there was no contributions from this meteor, and analyze just as many spherules as you
So
collected
100
in the
kilometers away or something, and drag
1,000 kilometers away in a different ocean.
Right. Going to need
My
another $1.5 million though, Larry.
my guess is that the researchers who focus their work on micrometeorites and cosmic spherules would love for these people to fund an expedition somewhere else in the world and collect spherules, dredge it and collect spherules. And my guess is if they did that somewhere else, they will find, out of 50, they'll find 5 spherules that have a different unusual composition. It's just there's the chemical diversity at this scale on the Earth and in meteorites is so huge that you're going to see it on this scale. And comparing the compositions of tiny, tiny little blebs of material to bulk compositions of rocks and planets, and then drawing conclusions about magma oceans and things, it's just not a valid comparison.
And again, you're not saying that this is definitely, we've definitely got a flat distribution or anything. It's just that the evidence that we've been shown can't tell us that we have an enrichment along this path. We just don't have the information. So
yes, that is the correct. We do not. There's no evidence to support that they are in higher abundance along this path.
So, Steve,
I want to
jump in?
Yeah, I mean, if you were to try to get this funded through a federal funding agency where they actually have safeguards to not waste the taxpayers' money, you would have to have a conclusive result at the end of your experiment. And we're in the business of testing hypotheses. And you would try to have two competing hypotheses that make different predictions that a measurement would distinguish between. That is the basis of science. And in this case, you would have the assumption or the hypothesis that there's just a background of objects that are kind of worldwide and not anything to do with this particular meteor. And the alternative is that they're definitely associated with this. So you would design an experiment where you would
that can distinguish between those two hypotheses, and this just can't.
And this can't. We're left with a very inconclusive result, and some funder is out a few $1 million.
Yeah. So I mean, to summarize for kind of people who are watching. So given the current data that we have, maybe they have more data, but we simply haven't seen it. We can't be certain that IM1 is an interstellar meteor. We can't be certain that it didn't just burn up. We can't be certain that Loeb's team looked in the right place. We can't be certain that they found spherules that actually come from IM1. And even if they did, we can't be confident that those spherules are of an extrasolar origin given their composition. So all of those kind of 5 pillars that you talked about at the start, none of them have kind of really been ticked off. Maybe we can say some of these come from space with some degree of kind of certainty, but that doesn't really get us anywhere when we're talking about going extrasolar rather than just extraterrestrial. So I want to kind of go a little bit broader, and just before we move off the analysis, what would you say, Steve and Larry, was your expert assessment of what we have with these spherules, particularly the ones that look a little bit odd? Would you just say that these are generic spherules that probably came from space and have interacted with the rocks on Earth? What would you say we can see from the evidence that we've got? What would be your call?
Yeah. Well, I think a much more mundane but plausible alternative hypothesis is that there is a background of cosmic spherules from micrometeorites that have just reacted via seawater with the sediments they're in. They have a lot of time to do so. In this particular region, the sedimentation rates are very low, and so micrometeorites remain close enough to the surface to grab for possibly 50,000 years. Different places around the oceans have different residence times, sedimentation rates, and they have different sediments with different chemical compositions. But it seems quite reasonable that in this place you had some extra time to react with the sediments. And that's a very, very plausible alternative hypothesis. It's what Rudraswamy and Prasad concluded about the cosmic swirls from the Indian Ocean. And so that's the first thing you have to check and rule out.
Larry?
I agree 100%. I think they're likely meteoritic in origin, but from the solar system, and have interacted with the Earth.
Fair enough. Go on, please, Larry, continue.
I was going to say the one thing that I actually wish they had done, and that they would have, that would be much more compelling, would be to measure the oxygen isotopes of these spherules, where you expect much larger variations in the solar system than in iron isotopes, and could potentially give much more information about where they're from. And they, for whatever reason, did not do this, despite oxygen isotopes being known as the key discriminant in the isotope space of the solar system.
So just before we finish, I want to come on to kind of wider context, the kind of wider scientific context and maybe the social context. So do we expect this analysis to get through peer review in its current form? I'm guessing neither of us expect that. It's going to need significant further work to be able to kind of get through that gauntlet. Steve, if I come to you first.
Yeah, well, it shouldn't. There's a number of issues, pretty obvious issues, because I'm not an expert in cosmic spherules myself. I know some cosmic chemistry, but if I could find this quickly, I should hope a competent reviewer would find these and many others. It's been delightful to see how my peers have each found some other aspect. It was Seth Jacobson who pointed out to me the iron isotopes indicating solar origin.
Yeah.
So I think that competent reviewers should be sought. Now, that said, it is my experience that the peer review process is pretty good, but it is not perfect. And so you always run the risk that papers are not properly reviewed.
Larry?
Yes, I think any competent review would reject this paper in its current form, and I'm not sure what it would take to make it acceptable for a reputable journal. Now, there are plenty of journals that will accept almost anything, but I'm guessing that Professor Loeb won't go too far down that road. In the past, he's just there's a history of papers not passing peer review, and then just going directly to the press and writing books and doing press tours to discuss the results, bypassing peer review. And perhaps he'll do that, maybe not.
So it seems, Steve, that there really are some glaring and obvious errors in this. So listen, I'm a particle physicist. I'm not an expert in this area at all, but the Poisson stat seems a pretty glaring problem, straight out of the box, a very simple statistical problem. Why, if this paper is so flawed, this preprint is so flawed, how did we get here? Is this just a case of not engaging with relevant experts in the field who deal with micrometeorites? How have we got to this stage?
Yeah, I think there are two issues. Loeb has a pattern of doing two things. One is, I think, as a theorist, I often try to construct a model and make it plausible, and get the idea out there and make testable predictions. but he seems to be stuck on the idea that all he has to do is make this a plausible. Well, maybe it was interstellar, maybe it didn't burn up, maybe,
So it's
and it's
kind
a
of
long
just asking questions kind of approach.
yeah, but and that's fine to construct a model and say, well, and if that were right, then you should be able to do this and this
Sure.
and but you always have to consider the alternative hypothesis and see what those measurements would do, and certainly refrain from declaring victory or drawing conclusions before you've gone through that process. The
Is
other,
this a case of him being that, just before you go into the second point, of him being so focused on this big idea that nobody's looking at, it could be aliens and the Galileo project? Is the problem that everything gets kind of filtered through that lens, so immediately the possibility that this could be something is such a huge deal and not something other people are looking at, that it kind of almost, he's like, I need to get this out there because it's so important for that kind of wider goal of looking for extraterrestrial life.
yeah, he feels that the community doesn't consider these things,
Mm.
and they should. And um, it shows a ignorance about what the community thinks about and considers. It's not that the community wouldn't consider this. There's people who are looking for interstellar meteors. They've been looking for decades. They've been analyzing radar data. They've been looking at optical networks. I mean, people are very interested in this, but we know that there's more than a plausibility argument is needed. If you want to establish that, an interstellar meteor crashed onto Earth, then you have to rule out these alternative hypotheses. And it's just due diligence,
Yeah.
So he
And
seems stuck on making it seem like, well, this is possible. Why aren't you considering this? And yet he's ignorant of what we're doing.
Larry?
yeah, I mean, I don't want to delve too much into issues of
No, of
psychology
course not.
and sociology. And to his credit, Loeb, at least for this paper, enlisted real experts. I mean, Stein Jacobson is a leading geochemist. The isotope and elemental measurements are very top notch. But strangely, and this is typical, he did not engage any experts in cosmic spherules and micrometeorites. And there are people around the world who have devoted their careers to this, who know a lot. And as you said, it took 10, 20 minutes of Googling to find the Rudraswamy paper with similar compositions. And, if Dr. Loeb had said, just sent it to Matt Genge or Rudraswamy or somebody and said, hey, what do you think of this? They would have said, oh, that's not a unique composition. And it's interesting that he chooses not to do that, he chooses not to listen to experts or engage them.
So if you engage them, they can immediately say, oh, really interesting stuff. If he went to them and said, I found some interesting stuff, I don't really understand it. To me, it looks a little bit out there. Maybe it looks extrasolar. Then they would quite happily get back to him and say, actually, his paper looks very similar. Maybe go back to the drawing board, have another think.
Yeah.
It's this getting out ahead and making these kind of very, very strong claims before we've got rid of these alternate hypotheses. That's really the problem.
Yeah.
Yeah.
Makes sense. And I guess,
and it wastes tremendous amounts of time for people who would rather be doing research than talking about why this research is not up to snuff.
So that's kind of the question that I wanted to come on to, because many watching, and I've already seen it on Twitter, people are very excited by what Avi Loeb is doing. They're very interested in, the idea that there's UAP flying around all over the place. They're very interested in finding extraterrestrial civilizations. We all are. What are potentially the negative aspects of this? I think Larry, you just flagged up there that it sucks kind of all the oxygen out of the room, and people have to spend a lot of time kind of debunking this rather than getting on with their work. So is that really the major downside, Larry, as you see it?
Yeah, there were probably 50 more interesting and more important scientific papers actually published after peer review in the last week, but not every newspaper and journal covered them, right? They had to cover this peer-reviewed preprint for whatever journalistic choices they made to do so. And, there's really good, excellent science happening all the time in our fields and in other fields. And why the need to cover things like this? It's harmful, I think, to public perception of science to highlight this so much and suck the energy out of the room for what really is not very good science.
And
Steve?
I want to go on and say about my second point is whatever Loeb's successes are in the field he published in for many decades, he's made this sudden shift into meteoritics and planetary science with Oumuamua, with the Chicxulub impactor, with panspermia, and this interstellar putative interstellar meteor. And in each of these cases, the work he's done is very uninformed and very sloppy. He is not good at this. And yet he has a big megaphone. And so it seems like the community is forced to respond to these claims. I see people on Twitter saying, well, if you disagree, why don't you submit a peer-reviewed paper?
I saw that. That's the immediate because he's doing such interesting, exciting things that people, are really engaged with. There's a lot of reflexive kind of, well, why would you be worried about this? You must be hiding something. There must be, these amazing things out there that you're not interested in.
Yeah, but
self-protecting almost.
Yeah, I know. I've been accused of gatekeeping, or I've been accused of being jealous, which no, I'm not jealous. But the fact is, I just don't like sloppy science, and yet the normal channels for correcting errors in the literature are very difficult. So in February of 2021, Siraj and Loeb published in Nature Scientific Reports a paper claiming that the Chicxulub impactor that struck the Earth 65 million years ago and led to the demise of the non-avian dinosaurs had to be a comet, and they basically presented a spurious argument. Basically, it's all based on the claim that comets have a good chance when they go around the sun before they hit the Earth of fragmenting into n fragments, and if n was very large, this increases the probability that it was a comet. It doesn't actually say anything about an asteroid. An asteroid is still the only thing that matches the iridium content.
So it's finding a little chink, one little thing, and then kind of riding it all the way through and ignoring the other.
Yeah, they ignored a lot. They ignored a lot for sure. They ignored some of the most important geochemical evidence that led Alvarez and Alvarez to conclude that it was extraterrestrial in the first place. The iridium, they're completely ignorant of it.
Anomaly hunting. That's what I was searching for.
Yeah, but worse than that, they claimed that n number of fragments that a comet breaks up into was 1,000. And I tried to follow up on this because that's not how many Shoemaker-Levy 9 broke up into, which was like a dozen. And you follow the literature in the Hand-and-Wright paper that they cited, and you go to the graph, which tells you how many fragments it breaks up into, and it's very clear. It breaks up into 15, not 1,000. And so they're 2 orders of magnitude off. And it's very difficult to read in the paper how they made this mistake, but it's just a really boneheaded mistake. And the number is completely wrong, but this is published. And now this is in the literature, and it's a refereed work, not well refereed, but it's a refereed work that's in literature. And now people will cite that as if that were right, and it's not. And yet we submitted a comment, my co-authors and I submitted a comment that somehow inexplicably had to go through 4 rounds of review with 6 referees. And the original paper should have been retracted. But instead, we had to run this gauntlet, and took 15 months. And so now that's at least in the literature. And if you read their paper, you might get linked to this comment. But it's very, very hard to correct these mistakes. Yeah. And it's these sorts of mistakes that once they creep in the literature, fuel further mistakes down the line. And so fine, I'm gatekeeping because I don't want sloppy mistakes to be in the literature.
Well, I was going to say, Steve, just to kind of, it's kind of the last bit I have before the sum up. Avi has kind of pushed back against you personally. I've seen on the Brian Keating podcast that I watched for some grounding on this. So he claims that you make him feel unsafe. He had to turn down a talk at Arizona State when he found out that you would kind of be running it or looking after him. So I think he feels that you're abusing him or harassing him. I think he's even pointed to some ideas that people might be coming after him because due to anti-Semitism or jealousy or closed-mindedness, as you said, lots of different things. What do you make of any of these claims that really people are coming after Avi because they're jealous, and this is just
Well,
abuse.
yeah, I did see the Brian Keating broadcast. I think I don't know who is conflating anti-Semitism with scientific critique. I will not deny that there is anti-Semitism in the world, but I don't see how it's relevant to this argument. The Arizona State, he was invited to give a virtual talk. So it was virtual. I wasn't about to go all Tanya Harding on him through an in-person visit. He was invited to give a virtual talk, and I asked Paul Davies, who invited him, if I could also speak at the same event to provide some balance. And so Paul agreed. And as soon as it was clear that we would both be speaking about Oumuamua, he backed out. And I don't know why, but I hardly see where I threatened him. He shouldn't feel threatened for his safety. Perhaps the safety of his arguments are.
Which is something he claims to welcome, right? So that's not a problem.
He has claimed that if anybody were to show him an alternative hypothesis, he would tear up his paper and admit he was wrong. But at the first instance that he receives criticism, that's shown to be not true.
Yeah.
Okay, let's round this up then. So Larry, where do we go from here? What is the correct path for us to take with this? If Avi Loeb wants to carry this through, and he wants to insist that we have an extrasolar meteor here, and he has found spherules from that extrasolar meteor, where do we need to go? What does he need to provide to the scientific community to make that case?
He needs to publish his results, get them through peer review, and address all the arguments people have already made. I mean, this is already peer review. It's just in the pages of podcasts and Twitter and Science Magazine and the New York Times. He needs to address these issues head on. I mean, the correct approach would have been for everyone to ignore it. Say this is a preprint he put up on the same day without peer review. He put up the same day he's releasing a book, so he knew he would get attention and sell it, and it worked. I mean, the correct approach is a better approach to science journalism in our culture writ large, but that's not going to happen. So the correct result, or at least it didn't happen in this case, the correct result now is for him to get the paper published, and it would be really, really excellent that if it never does get published, if it fails peer review, for the same people who've written breathless news reports about it to write a new report correcting the old one.
Yeah, it's tough, right? Because we in the journalism, people want to follow these, exciting stories, but then it's boring for them, quote unquote, boring to correct the record afterwards. Nobody wants to kind of read about that.
I've gotten at least one request for comment from a science journalist that said, I really, really did not want to cover this, but I am told to. Yeah.
And the corrections do not happen. And regarding Oumuamua, some wag said, looks like a solar sail goes around the world before a nitrogen iceberg gets its boots on.
So Steve, in terms of the science, is there anything he can do to kind of clean this up? I guess he needs that control sample, right? He needs to get the another 1.5 million and go drag it around the Indian Ocean and get the control sample of spherules somewhere else to even kind of start on this.
Yep, that would help.
The next step would then be when you extract the spherules is to prepare them in a way where you can measure their oxygen isotopes on a small amount of the material. You don't need that much. These things are like 30% of the mass of these spherules is oxygen, so you don't actually need very much material at all. And so you know the oxygen isotopes of all of them, and then take the rest and do the other isotope systems and the trace elements and see what you find. But in the rush, you don't rush it and do the things you can't, they did the things they could do, so they did them rather than seeing what the right approach was. You do it systematically. You take the time it takes to do this. And for most projects of this sort, these are years-long research projects involving lots of people and lots of tedious work. And at the end of your 3-year project, you write the paper and you submit it for peer review. And if it gets accepted, you've convinced it's an important enough result, you write your press release.
It has gone very quickly from I'm going to go on a boat to I'm on a boat to I've written a paper about what I found on my boat. I was like, that wasn't that a couple of months ago that he came back. I was like, just from my experience in science, you know,
and they sacrificed
6 months or something to get the paper, you know, into a decent state.
They spent $1.5 million or whatever to get this really interesting set of objects, and then destroyed them to do the mass spectrometry without thinking through what the right approach would be to get the most information out of them. They went almost straight to the most destructive step.
Is there no chance they can go back and do more analysis? I don't know. They claim to have more spherules, so maybe they can do more analysis, but unclear. I guess this hasn't been presented.
If they have, I don't know. I don't remember what they said about how many spherules they collected. If they have more, maybe they'll do what I'm suggesting.
I think they said they had a few hundred, I think.
Oh, then.
But they're not all interesting ones. I don't think. I think some of them are just boring ones, I guess, because they don't seem to have made it into this analysis.
There's probably a limit to how much they could do on the time scale before his book came out.
I'm not touching that.
Yeah,
Steve, do you want to sum us up?
Yeah, Loeb has definitely been dismissive repeatedly about the expertise of people in this field and the peer review process. You know, we have the word submit a paper. You submit a paper to peer review and you put it out there, and you have to accept the judgment of your peers, and you cannot take a negative judgment and claim that people are being closed-minded or that they're mediocre scientists if they aren't jumping to the same conclusions you are. And you have to internalize that you can improve the paper and that you can fix mistakes and learn from the experience. We use the word submit a paper. What Loeb does is just post these things on archive, go to pay-per-play journals, avoid peer review process for funding, and at every step of the way just looks for a particular answer. He knows what answer he wants to find, and so he finds it. And that's not how science works.
I think that's a really good place to leave it. Steve, Larry, thank you very much for taking the time this morning for you, this evening for me. So I really, really appreciate it. Anywhere that you would suggest or like to point people to keep up with the work that you're doing, or any other work on this issue? It's a free, open space for you to point to anything you'd like.
It's funny because I'm trying.
Have you got a book out, Steve? You got a book you want to talk about?
No, I don't. I'm trying not to work in this field because it's mostly.
I'm going to put Steve's Twitter thread up here. So if you want to go and give him some abuse, it's down below. There you go.
Yeah,
I'm only joking. Be nice. Be well behaved.
I don't know. Feel free to Google me and read my papers. I post them on a website after they've been through peer review.
I definitely need to have more of a web presence with my own work. Yeah.
Well, if you want to send me any links afterwards, I'll make sure they're down in the description. I'll make sure links to your kind of research gates are both there as well, so people can follow up on the work you're doing and the excellent Twitter threads you've done on this topic specifically. So I'd just like to thank you both again for taking the time. Hopefully when we get a little bit more resolution on this, we can get back together and have another chat. It's been a great pleasure, and I've enjoyed it as well a lot. It's been fun. I'm also I think I'm probably going to work this up into an explainer. So I might come back to you this week and say, Steve, Larry, is what I've written sensible, or have I completely missed got the wrong end of the stick? So I might do that later in the week if you're happy with that.
Well,
I can't promise I'll have time to look at it.
I can bug you regardless. Don't worry. And
if I never watch it, I won't be bothered by what I see.
But thanks for letting us make the case in a very well-paced and reasoned way and get all those points out there. And you've summarized everything we said very nicely, and I thank you for that.
So Larry, Steve, I'd like to thank you again for taking the time. When we get more clarity on this, let's get back together and have another chat. Thanks
Thank you.
Take care.
Thank you very much.
Bye now. Bye. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.